at this particular time, even I am feeling tired about talking about atoms, right? Enough atoms, right? So, but still, I have very important part left out. That is the last part which is left out of atom is nucleus. So, just for the one last time, it's just the last drill. Let's get on with the last part of the atom, nucleus. What exactly it is? What are the phenomena associated with it? How do we disturb it? How do we use it as human? Let's find out. Now let's study the last topic of our interest in this chapter of modern physics, that is nuclear physics. Previously, that is previous to this topic of nuclear physics, whatever we have studied, it was concerned to the atom as a whole. How the atom was arranged, what were inside the atom, and how can we, probe through light what is the structure of the atom, how it will behave, the spectrum, the light it reflects, and so on and so forth. Right now, we are getting inside the atom. That is going to the point, the rigid point at the place at the center of atom, that is nuclear. We know that the structure of the atom by now is, there is a hard positive nucleus center at the middle of the atom. Around that, the electrons are moving in indefinite shells, right? Stationary orbits. Now, this is a structure of an atom. So, if I want to draw it, it will probably look like this. So, this is by far the structure of the atom which I can come up with based on the different evidence which I have got. Now, I want to study about this. So, this is nuclear physics. That's what we're going to do right now. So, let's dig into what is or what are the few facts about nuclear. Now, this nuclear physics, it came into existence when I was, or let's say the humankind, in the face of Henry Becquerel, discovered the radioactivity in certain materials. So, what he saw is that the radiation actually blackened the photographic plates when he kept a few of the substance nearby the photographic plate. So, and he also came to conclusion that neither the temperature, pressure, or any sort of chemical reaction or the combination related to the matter affects this phenomena. That is, if I have two substances, if I mingle them up and then end up giving me a particular compound, or let's say a mixture, nonetheless, what's the temperature, what is the pressure, I don't give a damn about it. What I witnessed is they were blackening the photographic plates at the same rate when they were placed separately. So it means the property is to the very core of the atom. That is, it is not affected by the environment. So the environment, the environmental factors, they only affect the outside of the atom. That is the way the electrons move and in which orbits do they move. So that is, or let's say, the effect of external factor is up to that limit. Now internally, it's very safe and sound place. So any phenomena which isn't affected by the external environment, I straight away make or let's say start to correlate that it has to be associated with nuclear, something present at the center of the atom, which is unaffected by the environment. That was the conclusion which we came up with, and hence the birth of nuclear physics. Now, what we observed is there were the three types of rays which came out whenever there was some activity inside the nucleus. That is alpha rays, beta rays, and gamma rays. So now what we will do, we will dig into these first and then try to retrace our way back of how we end up getting alpha, beta, and gamma rays, what are its properties and how can we use it. Now, first up is alpha particle. So alpha particle is nothing but a helium nucleus. That is, it contains 2 protons and 2 neutrons. Now, the velocity of the alpha particle which we usually get is 5 to 7% of the velocity of the light. So whenever there is a radioactivity associated, some sort of activity going inside the nucleus, they pop out alpha particles or 2 now and then. Now that is 1/20th of, or 1/20th of, or between 1/10th and 1/20th of the speed of the light. So it's pretty fast. So those have a very little penetrating power into material medium, but they have a very high ionizing power. So as I am big and fast, but I'm occupying a decent amount of space, so I I'm not able to move, me as an alpha particle, I'm not able to move through the material. So I have less penetrating power because of my charge, because of my mass. But because of the charge which I have and the speed with which I move, to the distance which I can move inside the material, I have good ionizing power. I can ionize the surrounding in which I'm moving. So these are the properties of alpha rays. Now, next up is beta particles. Now, beta particles are simply the electrons moving at high speed. These have greater, compared to alpha particles, the penetrating power but less ionizing power. Their emission velocity is almost the velocity of the light. Like alpha particles, they have the spectrum of energy, that is, beta particles possess energy from a certain minimum to a certain maximum value. Now, I've just read out all the sentences present in the slide. So I'll explain you what I'm trying to say. Now, beta particles are merely electrons. Now, imagine I have eaten something, right? And it's unable, or let's say I'm facing some difficulty in swallowing it up. So I'm right now coughing it out. So right now I was chewing the food and then I was trying to swallow it down, or let's say thrust it down to my throat, but I wasn't able to do it. Now I'm coughing it up. Now the food particles inside my mouth, they are of different size, right? So if I spit it out, the one with the smaller mass will travel the fastest and the farthest. And the one with the big chunks, they don't travel pretty fast and they don't go pretty far. So that's the same thing happening. So whenever there is unrest inside the nucleus and I end up throwing a helium nucleus, so that is a big chunk. So my atomic mass is close to 200. I'm throwing out 4, right? So it's like, close to 25% of it. It goes 5%, so it's pretty big. So what we do is, when we cough out electrons, it is very, very small as compared to the mass of the total nucleus. So it moves like hell. It moves close to the speed of the light. And thus, it has a very good penetrating power. Second up is, it has low ionizing power because it's too fast. But the other case is, it has one negative charge. So, that's the problem associated with the beta particles. It is very penetrating, but it's not able to ionize that much. Now, the other important fact is they have spectrum of energy that is related to, the speed with which I can throw up. They have different wavelength associated with it. So they have maximum and the minimum, let's say, energy available when I'm coughing up beta particles. So they have that. And another fact which is not given over here is beta particles, they are chucked out when neutron disintegrates into a proton, which becomes a part of nucleus, and electron which is thrown out. Now, gamma rays. Gamma rays are basically electromagnetic waves of the wavelength 10 to the power minus 12 meters. These have the maximum penetrating power, even more than the X-rays, and the least ionizing power. These are emitted due to the transition of excited nucleus from higher energy state to lower energy state. Now the same thing happens inside the nucleus. This has been postulated that nucleons, that is the member of nucleus, protons and neutrons, they are arranged in shells which are very small in nature but is of the same nature as the atomic orbits in which the electrons are moving, the big atomic orbits. So whenever a nucleon is making a transition inside the nucleus from a higher energy state to a lower energy state, it loses energy. The magnitude of the energy which it loses corresponds to a light of wavelength 10 to the power minus 12 meters, which is called as gamma rays. And they are very penetrating, a good amount of penetrating power. That is, if there is a radioactivity material which is throwing out gamma rays, I need to put it in a chamber of lead, a lead which is kind of 1.5 meters thick in each direction, so that I'm not affected by those harmful rays. So imagine a small radioactive material kept in a safe, big, thick safe. Now, I've also told you the reason why there is an emission of gamma rays, and it has the least ionizing power. The reason behind the least ionizing power is I don't have any charge. I don't influence others because of some attraction or repulsion. I only influence or charge or ionize a body depending upon my speed. So I don't have a decent speed. I do have a very decent speed, but I don't have any charge. So charge kind of triumphs over the momentum, the mass factor. So hence gamma rays good penetrating power, but close to no ionizing power. Now, moving on, the simple rule of radioactivity, which was kind of empirical in nature, is during alpha decay, the daughter element was always 2 positions below the parent periodic table, because I'm cuffing it out, let's say in a helium nucleus, right? So this is the helium nucleus and alpha particle over here. So the mass will fall by a factor of 4, that is -4, and the atomic number will also fall by a number of 2. So that's pretty evident, because loss of alpha particle is 4 nucleons, that is 2 protons and 2 neutrons. Now during beta decay, the daughter nucleus had the same mass number, that is the atomic mass didn't change, but my atomic number sort of increased by 1, because I had a number of protons and b minus a number of neutrons. Now one of the neutrons degraded into proton and electron. So now the number of protons are a plus 1. What are the number of nucleons? Still b, plus an extra electron was chucked out or thrown out, and that is my beta particle. Okay, so that's how that's the effect of alpha decay and beta decay. Now, the gamma emission did not result in the change of atomic number or mass number. As we know, the gamma radiation is only because of a transition from a higher level inside the nucleus to a lower level inside the nucleus for a nucleon. So radioactivity over here is completely random. It's not governed. We cannot find a pattern or the effect. It can be predicted when a particular nucleus will decay. We cannot predict it. One can only discuss the probability of its decay. That is, if I'm throwing out 10 nucleons, if there are decay of 10 nucleons through a minute, in other there's 5 nucleons, I can only predict what will be the amount left. I can never predict what will be the nature of the atom, nature of the nucleus, what are the changes. It's completely random. There's no proper basis on which the events are unfolding as far as gamma emission are concerned. Now, what is the radioactive decay law? Now, the number of atoms disintegrating per second is directly proportional to the number of atoms n present at that instant. Now, it's the basic rule of radioactivity is the rate at which a disintegration is happening is directly proportional to the population of those who are disintegrating, which can be given over here. That is dN by dt is equal to minus lambda n, because as I know the number of particles are decreasing, so hence the negative sign. So if we solve this differential equation, we will end up getting the population of the system at any point of time, that is n is equal to n naught e to the power minus lambda t. That is the population we will end up getting. Now next up is I have these graphs, just plotted those functions over here. Again, this is the expression which we are looking for. Now it has been expressed in 2 different forms. Just a graphical representation of what I mean. Now, a very important aspect is half-life, the concept of half-life. So as the name suggests, is the is a time span in which the number of atoms I started with decrease to half of it. So if I started with 100, I know I have 50. Now the time taken for that particular transition is called as the half-life of that radioactive material. So again, let's walk this through in a form of mathematical equation. So I substitute n naught by 2 in the general equation of the population, and I end up getting the half-life as 0.693 divided by lambda, lambda being the rate constant. It's the same lambda which we have over here. I guess you are comfortable with the derivation part. N is equal to n naught e to the power minus lambda t. Now this is what we did. So lambda is the same rate constant which we have been discussing for a while. And I guess you have learned the same half-life concept in chemistry as well. Now it's common, or let's say this is a common science, it's a common area for both chemists and physicists as well. Now let's study about nucleus. A proton has a positive charge equal to 1.6 into 10 to the power minus 19 coulomb, and a mass equal to 1800, close to 1800 times more than that of electron. Now, a neutron has no charge but is having approximately the same mass as that of the proton, but in a clear mathematical way, it has a mass greater than proton, slightly but still greater. Now, the number of protons in a nucleus is given, is known as atomic number, is given by Z, and the number of protons plus neutrons, called as the nucleons of an atom, is a mass number A, that is the atomic mass of the atom. Now, why I am stating the obvious fact about the nucleus and the atom is we are about to witness a very path-breaking event or a path-breaking finding in the field of physics, to be specific, nuclear physics. So it will be essential if I stated the obvious things first and then dig into what was the shocking evidence inside the nucleus. Now, a particular set of nucleons forming an atom is called nuclide. So again, I'm working out the obvious things, and it's denoted as this. The nucleides having same number of protons, Z, and different number of nucleons, A, are called as isotopes. So one with the same atomic number, they are called as the isotopes. The nucleide having same number of nucleons but different number of protons are called as isobars. Again, few of the terminology which you need to get through. Then the nucleide having same number of neutrons are called as isotones. So if I have same number of protons, I am called as isotopes. If I have same number of atomic mass, I am called as isobars. And if I have same number of neutrons, I am called as isotones. So just walking you through these obvious things. Now this is the event which I was actually talking about, the path-breaking event in the field of nuclear physics. Now, what is mass effect and binding energy? So, or how we end up getting this is, what happened is, I know the mass of one single proton up to a decent level of accuracy, and I also know the mass of the neutron and the mass of the electron with a very good level of accuracy. So let's say there is a radioactivity taking place. So let's say there are 30 neutrons, 30 protons and 30 electrons. Now, I know that the 30 protons, 30 electrons and the 30 neutrons will give me a particular amount of mass for an atom. Based on that, I can clearly say that this is the total mass of the nucleus. After that, the radioactivity occurred and it split into the different parts. Now, when there was a splitting, let's say it degraded into part A and part B. What I'm expecting is the mass of part A and part B will be exactly equal to, sum it up, it will be equal to the one I started with. But what I observed is there was a difference. Now, this was no normal mathematical error or let's say an experimental error. It was a decent error. That is, I know what was the level of accuracy which I had, and it didn't fall into the range of experimental error or measurement error. So it was definitely something, and that's what I wanted to have a look at. That is, what's happening? Oh, why is there? Oh, where is that different mass? Where did it go? What happened? So, based on that, we came up with the concept that the mass, sometimes they are not conserved. Sometimes it is converted into the form of energy. Now that energy which I am talking about is called as the binding energy. The mass is lost and the binding energy is basically the energy needed for keeping the nucleons at one single place. The reason behind me able to keep up the nucleons at one single place is the binding energy. I know that the protons are very close to the other protons and they're going to repel the protons, but still they are where they are at a very small distance away from each other. The reason is there's some other force which might be overcoming the electrostatic force of repulsion, resulting into the shape of the nucleus in a rigid structure. So I have a nuclear force expending binding energy and keeping the nucleus intact. Rather than exploding, it's keeping it intact. Now again, the mass defect is basically mass due to protons, mass due to neutrons, and mass of the actual product. So that is the energy which is needed, and this mass is converted or related to the energy released in this particular form, E is equal to mc square. This is energy which is released when mass is actually used up to make sure that the nucleus stay intact. So it's a plotting of binding energy per nucleons for different atoms. So you can see that it's around iron, that is atomic number 56, and more stable. That is, each nucleon is entitled to 8.5 mega electron volt, which is too much for keeping it at where it is. Again, so these are the few facts about the same graph which we found it in a purely experimental nature. Now the nuclear forces, again, they are a short range, because I know if they were of long range then the whole atom would collapse, but it's not collapsing, so it means it's short range. Obviously it's much more powerful than gravitational or any electromagnetic force. Second, they are independent of the charge. So I know that there is an attraction because the forces are independent of the charge. Both protons and protons and protons and neutrons are interacting. So next up is nuclear fission. So nuclear fission is a proper use of radioactivity, where the one single atom splits into many particles when you apply a small disturbance. So I have uranium-235. When I bombard it with the neutron, there is a split in the two things, barium and krypton, and a release of 200 mega electron volts of energy for one single splitting or one single decay of uranium-235, plus the release of 3 neutrons. So these 3 neutrons, now they are ready, they are capable of colliding with uranium-235 and then giving more number of fission. So it's like a chain reaction. I hit uranium-235 with one single neutron, it gives me 3 more neutrons. Now 3 more neutrons are in perfect alignment to hit 3 more uranium-235. Now after that 3, each one will give me 3, 3, 3. So I have now 9 neutrons. So it's kind of a chain reaction. It will keep on going on and on and on. So that is the reason behind the atom bomb, or this principle was used in designing the atom bomb, which we witnessed, sadly, unfortunately, in 1945 in Hiroshima and Nagasaki. So nuclear fission is the one which happens on the sun. That is, 2 small nuclei, they kind of join together to form a bigger one. So 2 daughters join to form a parent nucleus, or let's say the bigger one. So it's 2 helium molecules, 2 helium nuclei hydrogen nuclei joining up to find out the helium nuclei with the release of this much energy. Now the fact is, I need a good amount of temperature to make sure that this reaction takes place. So the temperature scale which I am talking about is in millions right now. It's like 3 million.
So let's study about a simulation corresponding to nuclear fission. So nuclear fission can be visualized as 2 nuclei in contact with each other and then somehow held by the nuclear forces, and they are a bit of an unstable. So let's say I have a nucleus of uranium-235. So it's shown over here in an energy graph that it is lying in a stable equilibrium, and the stable equilibrium is not that stable, as you can see that the uphill is quite near to where it actually is. So if I somehow give the disturbance to the combination of two daughter nuclei, which is represented by 235 uranium, it might be the case that they might end up overcoming this potential barrier. So that energy is given by a neutron. So if I throw up a neutron on a uranium 235 nucleus, it's split up. That disturbance is sufficient for making the or let's say the nuclei split into two pieces. Now, how we use this phenomena in generating energy, that is, we know that in this particular reaction the energy is released. So what we do is we make sure, that is, if you can have a look over here, I gave in one neutron and I have 3 more neutrons, so that these 3 neutrons can be used to split further uranium 235, and subsequently I will have more neutrons which will split up more number of nucleus. That is, a chain reaction will take place. So let's say I put up a nuclei over here. So this is uranium 235 nucleus, various nucleus is there, so I can reduce the number. So it's right now it's set up in 100, I can do it 75, 50, 1, 2. So let's start off with 25. This is a gun, splits up, right? So one single neutron was let's say sufficient enough to split majority number of uranium 235. So right now I have 3, 3, 10, and I started with 25. So it means I was able to simply split half of the nuclei with just single neutron. Again, let's say I take up to 50. Okay, this is not a good angle, so let's say I make sure I split it over here, so it hits. So there is a chain reaction, it all goes berserk. So right now you can see out of 50, I started with 50, now I only have 1. This is how uncontrolled the reaction can be when I'm dealing with the radioactive substance. So once I start up a reaction, and more the population, worse it is. That is, it will be totally uncontrolled. Let's say 50, let's start off with 75. So again you can have a look at it. It will simply go berserk, right? Again I am left out with 1. I started with 75, again left out with 1. So again you can see, if I'm increasing the number of population, the number of disintegration also increases, right? Again, let's say I put up a maximum of 100. Now this will be simply explosive. So this is how that neutron or nucleus bomb, which you have heard of, hydrogen bomb, this is what actually happens. Neutrons given in and split up, and simply results into tremendous amount of energy. Now as I know that the chain reaction is sort of uncontrollable, so I need to use that amount of energy. I know that a great deal of energy is involved and I want to use that. So the only way I can use that is to somehow control this chain reaction taking place. So that's done in a nuclear reactor. So a compartment is sort of created, so you can see that the nucleus are in separate compartments, and these are my cadmium rods which are responsible, as you can say, control rod adjusters. So these are basically the cadmium rods which actually absorb the excess neutrons so as to finish off the reaction. It doesn't get into the chain reaction mode. So I fire the neutrons, so small split, neutrons are absorbed before the chain can go any further. So again I do that, so some explosion over here and some explosion over here. So I just keep on doing that. So you can definitely see that the power output is increasing joules per second. So more the chain reaction, more will be the energy released per second, and I am not comfortable after a particular level of energy released per second. That will be destructive for me. It will create a blast. So again I just keep on doing that. If the rate of firing neutrons kind of increases, then the power output increases. So I don't want to do that. So definitely when anything is going around a nuclear reactor, it's controlled, that is the neutrons ejected per second, it's controlled such that the energy is also controlled. So once the energy is also controlled, I don't need to be bothered about some explosion. But you have come across different news related to some malfunctioning of nuclear reactor in Russia, in Eastern Russia, and also in Japan. So these are few of the problems which we are trying to deal with in nuclear reactor. That is, make sure that the control or the hold over the chain reaction is very sound. So that's the design of a typical nuclear reactor.
Let's do some problem based on nuclear physics. So, in which of the following decays the element does not change? Alpha decay, beta plus, beta decay, or gamma decay. So, I think we know that beta decay is just the conversion of neutron to proton or electron. Next up, in each fission of uranium-235, 200 mega electron volt of energy is released. If the reactor is 100 megawatt power, the rate of the fission will be. So I know that the total energy released per second is 200 megavolt multiplied with the number of atoms which are disintegrated is equal to the power which I have received, 100. So the number of disintegrations which took place in 1 single second was 100 megajoules per second divided by 200 mega, 1.6 into 10 to the power minus 19 joules. So if you work this out, it comes out around 3.125 to the 10 to the power 18 per second. That is the number of disintegration which took place, or the number of fissions actually which occurred. So 3.125 to 10 to the power 18 per second is the correct answer. Now I just came to know about the nucleus, everything about nucleus. What binds the nucleus, what destroys the nucleus, how the energy is released, what are the different types of reactions, so as to speak, which the nuclei undergoes, and how to our use I can have those kind of phenomena giving me energy for my own benefits. Nuclear reactors, nuclear fission, nuclear fusion, atom bombs, hydrogen bombs, these kind of things, I've totally understood that right now. These, on the flip side, it has some adverse effect, as I quoted, the different types of bombs, Hiroshima and Nagasaki bombings, very bad on the face of human history. Now, we are done with everything which we want to know about the nucleus. As I said, nucleus will be the last part of the atom which we will study. Now that we are done with the last part, I'm saying we have covered up modern physics as a whole. But still there's something left. What is it? We'll find it on the next video.